Hello and welcome to Mrs. Law's class. In this lesson, we're going to take a look at binomial probabilities. Now, before we do that, let me talk about all probabilities. So, not all outcomes for an event may have an equal probability. A list of possible outcomes and the associated probabilities is called a distribution. So, for example, let's say we have 2 red, 3 yellow, and 5 blue marbles in a bag. Well, the probability of each of the different colors is different because there are a different number of the colors in the bag. So we can draw a probability distribution using a graph, a table, or a formula that specifies the probability associated with each possible outcome in the experiment. And then from the distribution, we can then better understand an event. Now, let's take a look at what a binomial distribution is. A binomial distribution is the pattern of probabilities that consists of repeated, independent, and identical trials. That means that the sample space always stays the same. That means with replacement. Also, there are only 2 mutually exclusive outcomes per trial. So, for example, heads or tails, boy or girl, defective or not defective. Now, these values don't always have to be the same. Now, if we say that the probability of success is P, then the probability of the failure, or the thing that we're not looking for, is going to equal Q, which actually equals 1 minus P. Now, the term success refers to the outcome whose probability is to be determined. Any other outcome is called a failure. The terms success and failure imply nothing about the desirability of the outcomes. The binomial probability has a formula that we can use to find the probabilities when there are only 2 outcomes. So we can say that the probability of x is equal to NCX times p to the power of x, which is what we're looking for, and then times q to the power of n minus x. You notice that the binomial probability is related to the binomial theorem, but notice that the exponents are swapped. All right, so P stands for the probability of a success on a single trial. Q stands for the probability of a failure on a single trial. And then X is the number of successes and then N is the number of trials, which is how many times we are doing the event. Let's take a look at an example. So a fair coin is flipped 4 times. Determine the following probabilities. All right, so the probability of exactly 4 heads. So this is equal to, so we're going to flip the coin 4 times, so that would be 4. And we want 4 heads, so 4C4. The probability of a head is half to the power of 4. And then the probability of a tail is also a half. And then we have 4 minus 4. So these are the heads, and these stand for the tails. And then calculating this into a calculator, we get 1 over 16. Okay, what happens if we want exactly 1 head? Then we're still tossing the coin 4 times, 4C1, and now we have half to the power of 1, and then half to the power of 3, because those are the tails. So again, the first fraction stands for the heads, the second fraction stands for the tails. And then typing this again, we get 4 out of 16, which equals a quarter. Which makes sense because the head can appear 1 time, either the first coin toss can be the head, or the second one, or the third, or the fourth. So 1 out of the 4 times we can have a head. All right, what about the probability at least one head? Now we can think of this as one head, two heads, three heads, and four heads, but that's a little bit long. So we can also think of this as 1 minus the probability of having no heads. So to do this, we're going to go 1 minus, we're going to toss a coin 4 times, and we want 0 heads. So this will be half to the power of 0, and then half to the power of 4 minus 0. So this is 1 minus 1/16, and that gives us 15 out of 16, which also makes sense because if we want at least one head, the only time that we can't get any heads is when they're all tails. And that would be 15 out of 16 times where we have at least one head. All right, the next one we have probably at least 3 heads. So that means that we want 3 heads, or we want the probability of 4 heads. So to do this, we're going to go 4 coin tosses, see, 3 for 3 heads, times half to the power of 3 heads, and then we want tails, half to the power of 1 once. Or, meaning that we're going to add 4C4, half to the power of 4, and then half to the power of 0. So here we have 4C3, which is 4, and then here we have half to the power of 4, so that's 1/16, plus 1/16 here, so here we get 5/16. Let's take a look at another example where the probability of success and failure are not equal. So here we have a multiple choice test. It has 10 questions. So each question has 5 choices, only one of which is correct. So all questions are answered randomly by guessing. Determine the following probabilities. Okay, so the probability of exactly 2 correct. So that means that we have 10 questions and we want 2 of them to be correct. So getting a correct answer, the probability of that is 1 out of 5. So 1/5 to the power of 2 because we want 2 of them to be correct. And then 4/5 are failures, or the ones that are wrong, or the ones that we don't want. And that will be to the power of 8 because 8 of them are going to be incorrect. So typing all of this out onto a calculator, we're going to get 0.302. Let's take a look at the second example. Here we are looking for the probability at least 2 correct. So we want 2 correct, 3 correct, 4 correct, and so on, all the way to 10 correct. Now that will take us a long time to add up all of these individual probabilities. So a quicker way to do this is to say this is equal to 1 minus the probability of none correct, because we don't want any correct, and then we also minus the probability of 1 correct, because we also don't want 1 correct. So this would be 1 minus 10 multiple choice questions, see 0 correct. So the probability of correct is 1/5, and then this is to the power of 0, and 4/5 incorrect to the power of 10. And then minus 10C1, and then again 1/5 are correct, and we want 1 of them. And then 4/5 probability of incorrect, and we want 9 of those. So doing an in-between step, we can get 1 minus 0.107 minus 0.268, and then calculating all of this together, we get 0.624. So that's how we calculate a binomial probability when there are only 2 mutually exclusive events, and also when they are repeated, and each time we do the event, they are always identical.